For over 100 years now, physicists have been chasing this beautiful, singular dream, finding one single theory, maybe even just one equation, that explains our entire universe, everything from the tiniest particle to the biggest galaxy. But that dream, well, it's in serious trouble, and it's forcing some people to ask a really radical question.
Yeah, what if we've had it all wrong from the start? What if the universe isn't one single elegant story, but something a whole lot messier? Let's dive into why this one question is now at the absolute heart of a crisis in modern physics.
Okay, so the problem really starts here, with this fundamental conflict between the two absolute pillars of 20th century science. We have these two magnificent theories, right? They describe our reality with just breathtaking accuracy, but they refuse to talk to each other. Mathematically, they just can't stand to be in the same room.
And you can see the divide perfectly here. On one side of the ring, you've got Einstein's general relativity. It's the undisputed champion of the very large, planets, galaxies, the beautiful curve of space-time. Then, in the other corner, you have quantum field theory. It is the king of the very small, particles, forces, all that wonderfully weird subatomic stuff. The crazy thing is, in their own domains, they are perfect, flawless. But the moment you try to use them together, the math just completely falls apart into nonsense.
And this isn't just some abstract theoretical problem. It's that they break down exactly where we need them the most. Like what was happening at the moment of the Big Bang, or what is going on deep inside the singularity of a black hole. I mean, these are the biggest, most fundamental questions we could possibly ask. And to answer them, you need both theories working together. But they just won't.
So this epic failure, this breakdown, it gave birth to what is basically the heroic quest of modern physics, the search for a quantum theory of gravity. The dream of a final theory, or what some people call a theory of everything, that would finally bring the world of the large and the small together into one beautiful, coherent picture. And for decades, two main champions have really emerged in this quest. Each one takes a totally different swing at solving the puzzle. And you've probably heard of them: string theory and its biggest rival, loop quantum gravity. So string theory's big idea is, well, it's both radical and elegant. It says that if you could zoom way, way in on something like an electron, you wouldn't find a little dot. You'd find a tiny, one-dimensional loop of energy vibrating like a guitar string. Different vibrations create different particles. So an electron is one note, a quark is another, and so on. Pretty cool, right? Well, here's the catch. The math only works if the universe has 10, or maybe even more dimensions.
But this is where that simple elegance starts to get really complicated. See, as physicists dug deeper into the math, they found that string theory doesn't just describe one possible universe. It describes a vast landscape of possible universes. And how many are we talking about? This many, 10 to the power of 500. That is a 1 followed by 500 zeros. It's a number so cosmically huge it's basically incomprehensible.
And this leads us to the theory's single biggest criticism. I mean, think about it. If your theory allows for literally trillions upon trillions of different universes, each with different laws of physics, how could you ever prove it's right or wrong? It's so flexible it can explain almost anything. So you have to ask, has it stopped being science and just become metaphysics? Okay, so let's move on to the other contender, loop quantum gravity. It takes a completely different path. Instead of adding new strings and dimensions, it attacks the problem of space-time itself. It says that space and time aren't this smooth, continuous fabric we imagine. If you could zoom down to the smallest possible level, the Planck scale, you'd see that space-time is actually made of discrete, indivisible chunks. It's pixelated, like a digital photo. And this is actually a brilliant move because it neatly avoids those pesky infinities that show up in general relativity. You can't collapse to an infinitely small point if there's a smallest possible pixel of space. So we've got these two incredibly clever, mathematically beautiful ideas. But after decades, and I mean decades, of brilliant people working on them, that grand dream of a final theory is really starting to show some serious cracks. And this little report card kind of sums up the whole dilemma. For string theory, you've got this awesome idea of vibrating strings, but its fatal flaw is that massive landscape of universes, which makes it pretty much impossible to prove wrong. Then you have loop quantum gravity, and its idea of a pixelated spacetime is super compelling, but it's really struggled to explain how you get from those basic pixels to the world of particles and forces we actually live in. And the bottom line, the failing grade for both of them, no clear testable predictions. Not a single one.
And this right here is the brutal, frustrating truth that's at the heart of the crisis. Despite all the work, all the papers, all the conferences,
neither of these theories has produced one single unique prediction that we can go out and test in an experiment. Nothing we can measure to see if they're right. And what that means is that fundamental physics has been stalled, kind of wandering in a mathematical desert for decades without a map.
So, this complete lack of progress has led some physicists to come full circle and ask that radical question from the very beginning. What if the entire goal is just wrong? What if there is no final theory?
This brings us to a really interesting idea called effective field theories. It's a much more pragmatic, maybe a little less romantic, way of looking at things. Think of it like a set of maps. You have a street map for getting around your city, and you have a globe for understanding the continents. You don't need a single map that shows both continents and individual street signs, right? Each map works perfectly for its own scale, its own patch. This idea suggests that maybe reality is just like that. Maybe all we get are these different frameworks that work perfectly on their own scale. And that's it? Maybe there isn't one ultimate grand map that connects them all.
This whole crisis in physics forces us to take a huge step back and ask an even deeper question, one that's really less about math and more about, well, us. Why are we so obsessed with the idea of unification in the first place?
And this quote really gets to the heart of it. Is our search for a theory of everything actually being driven by the evidence, by what nature is telling us? Or is it just an echo of much older ideas? You know, a cultural inheritance? A desire for one single, all-encompassing truth that comes more from philosophy or religion than from science? Just think about the words physicists themselves use to describe what a good theory should look like. Simple, elegant, symmetrical, unified. These aren't really scientific measurements, are they? They're aesthetic values. They're judgments of beauty. But who ever said the universe has to be beautiful according to our particular human standards?
So this leads to the ultimate kind of meta question here. Are we actually discovering the deep truth of reality? Or are we just trying to force the universe to fit into a shape that our own brains find satisfying? Are we just projecting our own psychological need for a simple, tidy story onto a cosmos that might be, at its heart, fundamentally complex, messy, and disjointed? And that leaves us right here. After a century of searching for that one perfect book that contains all the answers, we have to seriously consider the possibility that we don't live in a universe with a single grand narrative. Perhaps, instead, we live in a grand library, one that's full of countless different beautiful and locally true stories, and maybe there is no final chapter.